Yeah, so hello everybody, I'm David Maidman at Control Software Solutions. I was actually supposed to be in person today, however I messed up my diary and I've got a school appointment, so so unfortunately I'm doing this remotely today. Okay, so just before I get started into the detail of this presentation, just to give a bit of context of why I created it in the first place. I was working on a project reviewing and working with some client code, and they had some bottlenecks in their application. They weren't able to process incoming data from another system, and the application was falling over. So what they did was upgraded the hardware, and they didn't see much improvement. So they upgraded the hardware again. So they went through phases of running on i9s, i7s, i9s, and then Xeons, and still they were seeing negligible improvements. And when they when we took a look at the resource monitor, it was a Windows platform, we could see that the machines were just idling. They weren't really doing anything, and our application wasn't able to catch up. So we knew we wasn't using all of the available hardware, and so the client asked me what was going on, and I had a stab at an answer, and then I realized that I didn't really fully understand why we wasn't using all of the available threads. So I went away, did a bit more research and some trials, and then came back to the customer. So this is a kind of summary of what I found, and perhaps what I should have already known but didn't. So I have made the assumption that other people didn't know some of this stuff, and that it might be useful. Unfortunately, there won't be lots of LabVIEW demonstrations today on this one, but hopefully it's still of use to you. So just to get started then. So firstly, going to take a look at how things, who does what in the system. So looking at the application, operating system, and then processors. Okay, I'll try to keep terminology common throughout. I'll try not to switch between CPUs and processors and get things muddled up, but no guarantees. Then we're going to look at how work actually runs, so how work is distributed to threads and cores. And then the main part of it really is then to look at threads in LabVIEW and understanding what LabVIEW is doing with the execution system. And then finally, going to give some tips on how you can customize that thread allocation, and then give some guidance based on what I found useful as we've gone. So just a little bit about me, and this hopefully is relevant. So as I say, I'm David Maidman. I'm a certified LabVIEW architect and CPI, and I've got over 20 years commercial experience working with LabVIEW, but I also first came across LabVIEW when I was at university, okay, where I studied electronic systems and control engineering. So going back in time a little bit, back to 1998. This is where I first came across LabVIEW, and at the time it was the main software tool that was used in the control systems labs. At the time as well, I hated software. And I didn't consider LabVIEW to be software. It didn't feel like I was writing software at the time. So yeah, that's where we were back in 1998. And at the time, we was working with LabVIEW version 5. So taking a look at LabVIEW version 5 and looking in the release notes, which I found online, LabVIEW 5 includes multi-threading. Okay, just to give a bit more context as well, on the same release note, we got a nice big warning here saying that LabVIEW is year 2000 compliant. So it was a little bit ahead of its time. I don't know if everyone remembers the Millennium Bug, but that kind of shows with the technology that we was working with back in 1998. To me, it doesn't feel like a long time ago, but things have changed quite a lot. So looking in the release notes again, so we've got this explanation of multi-threading, and this statement that using multi-threading, you can take full advantage of computers with multiple processors. Okay, so if we imagine this, our application, operating system, and then multiple processors in our system. Okay, however, in 1998, when this was released in LabVIEW, most desktops were single processor systems. Okay, so we still had multitasking, but yeah, we didn't have multiple processors. Okay, so typically at the time, the most common CPU was a Pentium 2, and that had one core, which was one hardware thread. So hopefully, as we go, I'll try to explain a little bit more about what these are. And in a way, this was my problem. So when I was at university and we was doing, as part of engineering, we had to do C and C++. This is the technology we was dealing with. So when we was talking about multi-threading, then we was working with one core. Okay, and my mind was still stuck in that, even though I'd continued to work with these systems years after. With the technology back then, yeah, so you did have Pentium systems with you did have systems with multiple Pentiums in there, but that was not kind of everyday desktops that we was using when I was at university. So very quickly, to show how things have come on. So back in 1998, as I said, we had single core, which meant one logical processor. So by 2002, when we're looking at the Pentium 4, that's where we introduced the concept of hyperthreading, which I'll come on to later. So there's one core, but that one core has two logical processors. Okay, so again, we'll firm up some of this later on. Then by 2006, we have the Core 2 type processors, where you have two cores. Okay, so and the threads can then run on multiple physical cores. And then as we go to the kind of systems that we're working with now, we've got lots of cores and lots of logical processors. Okay, so just looking at my current laptop that I'm presenting off today, sockets. Okay, so this is just from the Windows About screen. So sockets, one socket, that's one physical CPU package. Okay, we then have 10 cores. So these are physical cores within that single CPU. But we've got 12 logical processors. Okay, this is what the operating system sees. So it sees 12 these 12 processors, which we call logical processors. Okay, so what that tells me is that because we've got more processors than cores, then we've got hyperthreading in there as well. Okay, so before we go too much into how the work is distributed, just a very quick overview of, in our system, who does what within the system. So if we think about, if we've got a model like this, where we've got an application, operating system, and a core, whatever that architecture may be. The application implements the business logic, which is where we have our UIs and stuff like that. So that makes operating system calls through high-level APIs, and so we may want to save a file to disk, send a message, draw a control. Okay. The operating system takes those requests, and then it works out how to turn those into things that the CPU, the core, the hardware, turn that into instructions that hardware can actually deal with. Okay, because the hardware doesn't actually do anything complicated. So it can just execute machine instructions that it gets from the operating system, and they're very, very simple things like move this value, add these numbers, and so on. Okay. So just a final thing on this. So the way that I have kind of come to understand it was the application is where we define what needs to happen in our application. The operating system does the management. Then it then decides, it knows how many processors it's got. It then decides who's going to do what, how it allocates the work, and how things are scheduled. And then the actual execution is done on the processors. Okay, so how does this? How do things actually run? So if we've got multi-threading, we can have our application, and we can have different threads for different activities within the application. Okay, so I'm just thinking about a single application in this instance. And we can request from the operating system that, let's say, the data acquisition will run in a thread, the user interface may run in another thread, and so on. Okay, so it allows different parts of our application to run independently. It also means that we can then make use of multiple processors if they're available. Okay, but from the software point of view, from our application, things don't change. Okay, so we just still write our application that runs on the operating system. The operating system distributes the work. So going back to 1998, when multitasking and multi-threading became available, we had a single CPU, my Pentium 2. Okay, so my LabVIEW application would still request threads, a number of threads. We look at this later, but it will request threads for work to be done. What the operating system will then do is schedule this work and kind of interleave the different threads into instructions that can be executed on the CPU. So as an example here, we've got a single core. It's going to do an instruction from thread 1, then an instruction from thread 2, instruction from thread 3, and so on. Okay, so very simple example. Obviously, it's not necessarily that it just does one instruction from one thread then the other. The operating system works out how to balance all of this. So that was where we were with the Pentium 2 that I was using in 1998. As we said, in 2004, when the Pentium 4 came along, it introduced hyperthreading. And the way to think about this is, if you imagine a core as being a person and hardware threads as being the hands. Okay, so the way to think of this is you've got one person, two hands. So sometimes I can use both hands at the same time. So the example I've got here is I can stir a pan and my other hand could chop vegetables. Okay, so I'm using both of my hands, and I can do this so long as I'm not trying to use the same tool. So I can't use both hands can't access the knife at the same time. And so long as my brain can coordinate it, as long as I know how to do those two things. So if you give me something really complex, I might not be able to do that with two hands. I may need to use one hand. Okay, but that's the way to envisage hyperthreading. And what that actually is we've got a single core with two hardware threads. So there's two like execution lanes within that hardware, within that core. So the way that appears, the operating system actually sees two processes. So we call these logical processes. Okay, so there's a single core in this case with that has hyperthreading. So there's two execution lanes that are exposed. So what we can see here is as we go down in time, let me just pointer. So as we come down in time, we can execute instructions in both threads, in both hardware threads. Now, what you'll notice is I've got different color code in here. So we've got instruction 1, instruction 1, instruction 2, instruction 2. So what I'm trying to show there is the operating system has still created its software threads and then interleave those onto the hardware across the two logical processes. Then as we then get into 2006 and we have the Core 2 technology come on with our i3s, i5s, i7s, we actually have more than one physical processor. So this looks very, to the operating system, this looks the same really. Where we have here, we've got two physical cores. So we've got then we got our set of software threads running on those hardware threads, hardware executions. Okay, so how does this all kind of work in LabVIEW? So LabVIEW's got an execution system. So when people have been digging around in their VI properties and they go to execution, they probably will have seen the execution systems, things that we can change. And maybe you've tinkered with it, maybe haven't, maybe just seen it and always left it. But what this execution system does is it's a LabVIEW defined scheduling system that uses a pool of operating system threads. So we've got our hardware logical processors that are hardware threads. We've got our operating system, which has software threads, but then LabVIEW is scheduling stuff itself as well, working cooperatively with like each of the processes that it's running. But it can map its work onto multiple operating system threads that will then get put onto the hardware threads. Okay. So how many threads have we got to play with? So first of all, let's have a look at how many threads LabVIEW requests are our application requests. So when I've looked into this, there's lots of different answers in lots of different sources. What I've summarized is, and this isn't going to necessarily reflect everything, but as a rule of thumb, LabVIEW requests a user interface thread, so one thread for the user interface, two timer threads that are used internally by LabVIEW, a number of execution threads, okay, which I've referred to as the main worker pool, and then a number of additional threads for things like ActiveX and stuff like that. Okay. So if we put those the timer threads, which are used internally by LabVIEW, and if we put the ActiveX stuff to one side, we basically have one user interface thread and a number of execution threads, our main worker pool. Okay. So every application always has exactly one UI thread, and it handles the panel updates, inputs from user, some property nodes and thread unsafe calls, DLLs and stuff have to run in the user interface thread. The UI user interface thread also services the root loop. I'm not going to go into the details of the root loop and how DLLs and stuff like that work, but just know that the user interface thread is responsible for managing your user interface, but then there's other stuff that it does as well. And yeah, as I say, there's just one thread available for the user interface. Then we got our execution systems. So I said that there was a worker pool of n execution systems, and the execution systems that we have are these: 1, 2, 3, 4, 5. So we've got 5 execution systems. Standard, which is the default. So when you create a new VI, its execution system will be set to standard. Okay. Instrument IO, data acquisition, and then there's two others: other one, other two. Okay, so I've given them some comments here. So other one and other two I've labeled as being spare, kind of spare pools. Data acquisition is suggested for data acquisition and signal acquisition type tasks. Instrument IO is suggested for kind of visa serial type stuff. In practice, there's no difference between any of these pools. Okay, so the names are given as guidance to help you organize things logically, but you could put whatever you want. So the data acquisition thread isn't better for data acquisition than the other one, for example. Okay, so these are our execution systems that we get to play with. And then within the execution system, we have several priorities. Okay, so we have background priority, normal priority, above normal, high priority, time critical, and subroutine. So when we create a new sub VI, we use the standard execution system, and it creates it with normal priority. So the majority of VIs that we create will run at normal priority. Okay, so just before I look into so let's just skip on actually. So just looking at two of those priorities are special cases. So subroutines are a special case. It doesn't behave like the other priorities. So what a subroutine priority does is, if you've got a VI that's called a subroutine, it has a subroutine priority, when it runs, it will run in the calling thread. So there's no context switching. It will stay in the thread that it's been called from, and it will block the thread. So anything else that's waiting on that thread can't execute until the subroutine has finished its execution. So it's a way of getting it to run really efficiently, really quickly. I would use this with caution and reserve it for small, quick tasks. Okay, so in practice, there's very few times where I've attempted to use this, but understanding that it will block the thread is important, and it runs, as I say, it runs in whatever thread the call for the call chain. Yeah, so it won't switch to another thread. Okay. Background priorities, they don't normally have their own dedicated threads. Okay, so they actually will just run in the next highest priority, so normal, for example, and LabVIEW will use cooperative scheduling to put that low priority task and do it as and when it can. So let's put those two to one side. We're left with 4 normal priorities, 4 usable priorities as our worker pool. So what LabVIEW does is it will request a certain number of execution threads. So the theoretical maximum that we can have will be number of execution threads times number of execution threads is the number of execution systems times the normal priorities times the number of processors. So what that works out is 5 execution systems times 4 normal priorities times P, where P is the number of logical processors. Okay, we'll come back to this. So what we have usable is 1 UI thread and 20 times P, 20P execution threads. So our usable threads is 1 plus 20P. So if we've got a single processor like I had in 1998, we have 21 threads. Okay, so if we have 8 processors, 8 logical processors, we can have 161 threads, and then for 16 processors we can have 321 threads. Okay. So the number of threads that we request is greater than the number of processors. So the operating system will be doing some software threading within the operating system. So this is the screen that most people have hopefully seen. So the way that we can configure this is we go to the VI properties, execution, and then we have our 2 kind of execution environment, execution system settings. So we've got our priority and preferred execution system. So priority by default is normal priority, and our preferred execution is same as caller. So it will run in the execution of what was called. Okay. One note on that: priorities are elevated if called by a higher priority. So if we specify a sub VI to have normal priority and it's called by something that has been set to above normal priority, it will run in that at that priority instead. They'll be elevated. So I keep referring to the default settings. So what we need to remember is when we create a sub VI, unless we change the settings, it'll always be set to run same as caller, normal execution, and same as caller, the default execution system is standard. So if we start our main VI and that's set to standard, if we don't change any execution systems, everything that runs beneath will also run in standard. Okay, so that's where this is kind of the reason that the customer's application wasn't doing what they expected, and that's because everything was running in standard. So although they was upgrading their hardware, it was having some impact on the amount of available threads, but nowhere near what they thought it was actually going to have. So we could be using far fewer threads than theoretically are available. Okay. So if we take a look at this, just to think about how LabVIEW can run stuff in parallel. Any of these four VIs can run in parallel. This kind of this loop can run in parallel. So what we may be in a position where we request, or we have things that can be parallelized way beyond what the available threads for us to use are. If that's the case, if we run out of threads, so for example, if we're going through, we want to try and parallelize this to 1,000 and odd instance, what LabVIEW is able to do is it will still use its cooperative multitasking to schedule the work that it then passes on to the OS. Okay, so you can still use more threads than are available for the execution system. LabVIEW will manage that. Okay. So once we'd found out that there was a problem and that we wasn't using as many threads as, in fact, just before I do that, I'm going to go back 2 slides. So just because I forgot to include this later on. So if you remember the execution systems we said we had a standard, we had data acquisition, instrument IO, other 1, other 2. Okay, so what we might do is at the top level, so let's say this sub VI here, this DAC, we may go into that sub VI, we may go to its properties, we may change its execution system to DAC, and then that would mean that unless told otherwise, everything this calls would also work in that thread pool. Similarly, the comms, we may go in and we may set that to we may set that to be instrument IO, and then therefore, unless told otherwise, anything that runs within this sub VI would also execute within that thread pool. Okay, so just wanted to point that out before we talk about it a bit when we look at the guidance. So LabVIEW actually lets us change the thread allocation. Okay, so we have that theoretical maximum number of threads that we can use, 20 times the number of processors per execution system, but everything's only running by default is running in the standard execution system. So we can either split our application, like I just showed you, to run in certain execution systems, and it may be that we decide that one of those execution systems needs to have a lot more threads available. It may be that we want to keep our whole application in standard, and therefore we want to just make the standard execution system have a lot more threads available. So we can do this by making a change. If we're working in the development environment, we can make a change to our LabVIEW ini file. If it's a deployed application, we go to our application ini file, and we can modify that, and we can tell LabVIEW, this is how I want you to allocate threads for me. So to do that, within the file, we need to have a section called LabVIEW, and we need to set this parameter. Okay, so it's esys.standard and parallel equals, and we have different meanings, okay, for the value. So 0 means turn off multi-threading. Not sure why you don't do that. 1 just means default, so the 20p for each thread pool. I've read different things on this. I've not convinced myself I understand how this one works. I'll be honest about that. So this defines a higher number of threads to start. So n equals 2 to 8. I've not managed, even through trial and error, I've not been able to get a full understanding of that one. So when we get to questions, if anyone knows, please shout out. And then we have this setting -1, and what that tells LabVIEW is that we're going to use custom settings. So for my client application, I went into the application ini file, and the first thing I did was I said esys.standard and parallel equals -1. So what do we do from there? So we actually then need to build these ini file keys. So we have esys and then the execution system dot priority equals, and then the number of threads that we want to apply. So if it's in the standard execution system, we can omit the execution system part. If it's in the others, we have to have the name. So for example, it could become esys.instrument. And then pick the priority v high. Okay, so the priorities we can change. Normal priority is .normal, above normal is .high, high priority is .v high, and time critical is .t critical. Okay, there are warnings, by the way, on using these. I've not covered those. So just as an example, so this is pretend this is my client file. I've set esys.standard parallel equals -1. So I'm telling LabVIEW going to use custom settings, and then I've set some priorities. So esys.normal, I'm going to have 16 threads. Instrument .high, I'm going to set 1. So what I'm saying there is for the high priority thread in the instrument pool, I'm going to have 1 thread, but it's 1 high priority thread. So you may not need more than 1 thread. So don't always assume more than 1 thread is going to make it better. The work that you've done may want to execute in a single thread. So we can change the parameters like this. Okay. One thing I'd say is don't set priorities for your background threads. So as we said, they're designed to work in the next highest priority up from them. I've found trying to change the background priority to actually kind of crash the application on startup. So I found to omit that. What you'll notice is I've not got the full list of all the execution systems, all the priorities. I've got quite a subset, and that is LabVIEW will just use the default. If you don't tell it what the override is, it will just use the default value. Okay. Okay, so just some guidance of things that I found. So when you're designing your application, that's a good time to decide as subsystems what's going to run in each thread pool. So, for example, when I'm doing my top level data acquisition, that's the time to say, okay, this is going to run in the data acquisition system. Don't over allocate threads. So if you've got lots of threads that are when you switch between threads, you introduce something called context switching. So there's a time for the operating system to switch to that thread, do the work, and switch back. But do use multiple threads when work can genuinely be parallelized. Okay. A lot of the time, this may be that you can do it all within the standard execution system. So by default, so people, and myself included, I try to have lots of high priority things, and it caused me trouble, because if you've got lots of things that run above normal priority, you start to starve the UI thread, and your UI can become unresponsive. I'm not saying never make something high priority, but don't think it's going to solve all your problems. It may introduce others. And then don't try to plan a priority or execution system for all of your sub VIs. Just leave them as the default, and they'll be set to run within the caller. So they'll run in the same execution system as the caller, and they'll run at the same priority as the caller, unless they need to, unless their priority has been set higher. Okay, yeah. So I finished a couple of minutes early there, but has anyone got any questions?
I have one question. If I go back to slide number 45, if I'm right.
Yeah.
44, sorry.
Yeah.
Yeah. So when you set the execution system for all of those 4 threads, there's a top level VI which calls these sub VI,
yep.
right?
Yeah.
So what was the execution system set for that VI?
So this, by default, it will be standard. Yeah.
Standard.
Yeah.
But did you have to set it to possibly a UI or DAC or instrument IO? Because then that will be same as the caller, right? So that'll have a setting which says it's same as caller.
So if it's set to same as caller, so any sub VI that's set to same as caller, it can be called by different modules, for example, that are at different execution systems, and it will just run in that execution system. So if you've got a sub VI that's being used by 2 processes that are in separate execution systems, when it's called, it will just run in the execution system that it's called at that time.
So the main VI that we look at there could just be set to standard execution.
Okay.
Yeah.
But then each of the module main VIs, so the DAC module, the UI module, and so on, they can be intentionally set to a specific execution system.
Yes.
And then any sub VIs inside each module, by default, they are set to same as caller. So all the sub VIs inside the module will essentially take the same execution that was set for the module top level VIs.
So there is a top level VI which is calling these sub execution system as well, or sub VI. But that would be set as same as caller, right? So let's say if the top level is set as standard,
Yes.
then all these should ideally execute in standard as well.
No. So what you can, so the VI we're looking at, the top level VI, will be set as standard, but because in the VI settings of each of the main VIs, of those 4 main VIs, in the VI settings, you can override and you say, I want this VI to be in this particular execution system, and then all the sub VIs under that VI will by default adhere to whatever was set.
If it's set same as caller.
If it's set up same as caller, which is the default. So by and large, most VIs in the project will be same as caller. And that's actually a good approach, because essentially to transform an application, so by default, everything will be same as caller, meaning everything will execute in standard. And very quickly, we can change that by just changing the properties of 4 VIs, just that drop down in 4 places. You can actually change the thread allocation massively, very quickly with just 4 changes.
I've had a play with the execution system in my experience. To be honest, it's not been all that effective for my purpose. Predominantly, the LabVIEW execution system default takes care of potentially all threads fairly good.
Yeah, absolutely.
Sorry, carry on.
Sorry. Yeah, I mean, that's it. So I was a bit confused on what the top level VI will do for all these 4 sub VIs.
So just one thing to highlight about the top level VI. So let's assume that all of these are running. There's one top level VI that's calling this code here we can see, and that top level VI is called my application main, for example. When I create that, I don't have to go into that sub VI and say standard execution. If I leave it as same as caller, when LabVIEW starts, it will automatically put that in standard execution. And then in this example, I could set, the reason I've got 4 here is I was thinking I would set this one to run in the data acquisition execution system. This one, I don't know what I'll do about that one. I'll leave it where it is, because LabVIEW will decide when it has to run in the UI thread. So I'll leave that to same as caller. I'd set this one to instrument IO, and I'd set this one to other 1, for example. And then my top level stays as same as caller, so it's standard. And then when these will get distributed across the worker pool. And what I found with the application that we was unable to improve performance by upgrading the hardware, we then saw a big improvement by distributing. And when we went to Resource Monitor, we could see all of a sudden we had many processors that were now busy, whereas before we'd have like 2 or 3 processors going flat out and everything else was idle. Whereas by using this technique, we was able to spread the application across the hardware much better.
I have another question. So there is an option if you go to, I believe, tools, profile, find all parallelizable loops.
Yep.
How useful is to tick all the?
So okay, so it's a slightly you get it. So you do that to get a performance improvement, but the way you'd get a performance improvement, if you imagine this for loop, I could put these filters in a for loop for readability and convenience, because of I'm going to call the same thing over and over again. If I don't parallelize this, what LabVIEW will do is it will run it, it'll go round, run it again, go round, run it again. So all of a sudden, if that filter, let's say it takes 1 second to execute, and I go round 100 times, then it'll take 100 seconds for this to execute. So what I could do is I could say, okay, I'll put 100 instances of this in parallel. Okay, but that's going to be cumbersome on the block diagram, and also it's going to be harder to read, and it's not expandable. You have to actually go in and change to be able to run a different number of times. By enable parallelism, what we're telling LabVIEW is this stuff can actually run in parallel. So if this took 1 second and we had 100 channels to filter, it would take 1 second, because LabVIEW would split it into the 100. It split it into the 100 parallel instances. So we're telling LabVIEW to be clever. So we could lay it out for convenience like this, and then just say, well, actually, although I've laid it out for convenience, I actually want all of this stuff to run in parallel. And that's what we do here. So if you use VI Analyzer and you get it to find parallelizable loops, you may look at it and say, okay, that's going to be going around a few hundred times. We could split it. So yeah, it helps to find potential areas of improvement.
Yeah, but it was one case when the performance, usually the performance increases, but there were some cases where the performance totally drops. The program was slowing down a lot compared with without the parallel loop. So what was the reason?
So that is explained by the fact that depending on what's happening inside of the sub-VI, parallelism can happen or not. If you're trying to enforce parallelism when it simply cannot do it, you will actually end up with slower execution, because there's some overhead in terms of LabVIEW trying to break up this work into, say, 8 chunks happening at the same time. There's overhead with that, and depending on what you're actually trying to do with the loop, you can get more out of parallelized than this overhead. But if you cannot get any performance improvement and you just pay the price of the overhead, then you end up with worse execution than initially. And typically, if in your for loop you're using any sort of shift registers, then that means that no parallelization can happen, because iteration n needs to know what happened in iteration n-1. Therefore, it cannot just split them out into eight parallel loops or 16 at the same time. It needs still to run one iteration after another. So whenever you see a shift register, that's not really parallelizable. But even if there isn't a shift register, depending on what you're exactly trying to do, it still may not be able to do a parallel execution for you. So basically, it's a bit of an art to actually find out what can be parallelized and what can't.
And usually, well, I used to work with, I work with images, and usually LabVIEW recommend to parallelize the two, because there are two nested loops, and LabVIEW recommend to parallelize both. Is that recommended or not?
I cannot speak exactly to that. I haven't tried parallelizing two nested loops, but I think maybe just parallelizing one of them, maybe the outer one. If I remember correctly from memory, I think Darren Nattinger may have recommended that in a forum somewhere. You probably know Darren. Do you know Darren? He's very prolific in terms of his presentations online and so on. If you search Darren Nattinger presentations, you will see lots of very good tips from him, and I think one tip was something like that, to only parallelize the outer loop and not the inner one. But I think again, it's a case of trial and measurement and benchmarking and seeing whether it made a good difference.
I think so. I think actually with the if it can't parallelize a loop because if it uses a shift register, for example, I think that results in a compile error now, so it won't let you do it. The only difference to that is you can have if you can put a error, so you can create a shift register for your error, and then LabVIEW smart enough to know that it's going to merge all the errors at the end, so it'll let you do that. And the other thing where you may get a delay is if within the code that's executing, if there's a shared resource, I guess. Yeah, I don't know, but yeah, I guess could do a full presentation on the parallelizing these. Yeah, the biggest issue is say it. I find it hard word to say. Parallelize. Yeah.
Yeah, that's the challenge.
I quite like your presentation. It's really nice. The way you've made those images and everything is really nice. Yeah.
I take it, question. I take it the priority level cannot be done programmatically.
No,
I can't see how it would be done. I don't know why I'd want to do it, but I can't see how it can be.
I think most of these settings can only be set at edit time,
Yeah.
but once the code starts running, they cannot be changed anymore.
I meant by programmatic.
You can read programmatically what the settings are, because of we created a tool that would scan the application, and it looked for things that weren't set to what we expected them to be, basically. So we got a big map of how the application had been distributed, and yeah, learned a lot from that. So you can read it programmatically, but yeah, it sounds like you can't change it.
And I have a few more mentions to make, if that's okay. First of all, just to thank for the amazing presentation, David. It's Petru here. Thanks, it was really interesting. And just by chance, in the last few months, I've actually looked into a similar questions myself, because of the work I was doing for work. I was trying to optimize my Windows apps in the same way that David mentioned. So actually, a few points that might help everyone here in the room is to mention, I don't know, David, if it's possible to go to the slide that showed the VI execution settings.
Yeah, if I remember where it is. Oh yeah, let's go back. Oh, there we go.
That one, perfect, thank you. So one thing I would say is, first and foremost, make sure you are looking out for non-reentrant VIs you might have in the application, because that will, from a start, that can kill the performance of your application. Because if you have a sub VI that's reused in multiple modules, if that sub VI is set to non-reentrant, which is the default in LabVIEW, it means that only one copy can run at a time. So the other copies will be sitting there waiting for that one to finish, essentially blocking multiple. You might have, say, 10 modules running at the same time, but in fact, they have this common bottleneck that they all have to wait one for another, which is very likely not what you want. So top tip, I would say, make sure to change the non-reentrant execution to either shared clone reentrant or pre-allocated clone reentrant. If you feel that's a sub VI that's used in many different places, you most likely want it to be a reentrant, not non-reentrant. So that's one tip I would say. Second, in terms of the priority levels, which are normal priority, above normal, and high and time critical, those four priorities that David said are in the middle. What's important to note is that increasing that priority won't magically make the code run any faster. That VI won't magically take shorter amount of time to execute. So let's say if you have the sub VI that took 1 millisecond to execute, it will still take 1 millisecond regardless of the priority you set. What does change though is if the LabVIEW scheduler has, say, 2 or 3 VIs that are all waiting to execute, and it needs to make a decision which of the sub VIs to select and run next, the one with a higher priority will be selected. So it will still take 1 millisecond to execute, or however long it took. It won't run faster, but it will be selected ahead of other sub VIs that are waiting to run at the same time that have a lower priority, if that makes sense. It will be chosen out of the pool of what's running higher than the others. Now, in some applications, you might not have multiple things waiting to run. So actually changing that priority might not make any difference whatsoever, because it was the only thing waiting to run at that moment in time anyway. So I would mention that as well. And in terms of the priority, the bottom priority, which is called subroutine, I've become quite a fan of using subroutine in the last few months, because in the documentation, in the detailed help associated with that option, it says that whenever calling the sub VI in LabVIEW, there's a certain overhead that the compiler has to do. So imagine when you're calling the sub VI on the block diagram, there's there's some instructions that the CPU needs to run to enter that sub VI and then to exit that sub VI. It doesn't tell us how many instructions, how much that overhead is. It's probably very small. It's probably measured in less than 1 microsecond potentially, but still there's some overhead. But setting it to subroutine eliminates that overhead, as if what's inside of that sub VI is directly on the block diagram of your main VI. And so I personally, I like that idea, and especially for very small VIs that do, for example, computations. Imagine you have like a mathematical formula that takes some 2 or 3 measurements and applies some sort of FFT or some scaling to give you an output. That's a very good example of just one block of operation the fact that so the limitation of the sub-VI is that it cannot be aborted. Like once the code starts running, it needs to finish, and then other threads will be reallocated. Well, that's fine with me, because that's a kind of a very self-contained and isolated piece of code, that computation, that I don't want it to exit from that anyway, and that reduces context switching as well. It just reduces, if you have subroutines in your code, it means that the compiler can group more computation into longer threads that can run for, say, a whole millisecond on the processor instead of 10 microseconds, if that makes sense. So in the world of processors, 1 millisecond is a long time. There's like thousands of instructions there, but that reduces the context switching, and it just makes the whole application more and more computationally efficient. So personally, I think subroutine is actually underused in my opinion, because I hadn't used it until a few months ago, but now in the last few months I've become quite a fan. And in the VI lib, in the VIs that ship with LabVIEW in VI lib, if you dig down, there's some low-level VIs that ship with LabVIEW that are by default set to subroutine to begin with. So clearly, the people who created those VIs from N9, they thought, oh, this is a good example of a low-level sub-VI that might as well just be subroutine, just to give maximum performance to any application using them.
There's just to follow on from that. So the recommendation I've got is for small, quick tasks like calculations.
Exactly.
But the important thing to be aware of is, like you said, is when it's executing, it blocks the thread, so it can't be shared and with other activities that are going on, which may be what you need. In terms of the context switching and going to other threads, the other way to achieve similar thing is to use you can inline the sub-VI. If you inline the sub-VI, you won't have any context switching, because it will run, because it cuts and pastes the code, so you'll still be running in the same thread, but it won't reserve the thread in the same way that a subroutine works. That's my understanding anyway.
I've got what might be a bit of an odd question. When you've got priorities and you've got something which is at a very low priority, does it have an aging benefit to it so that it doesn't get starved? Do you understand what I'm getting at?
Yeah. So if it's low priority, so no, I think if you got things that are low priority and they're not given time, then you'll get starvation. Yeah.
Yeah. So I mean, it's the art of programming, I know. I just wondered if there was a facility to put aging in.
Sure, it'll be there in some sort of watchdog timer.
Well, the watchdog doesn't sort priorities out.
This is so that question is beyond my knowledge and expertise. From what I've done so far, I wouldn't be able to answer that one. That's beyond me. As far as from everything I was reading, it was saying about being careful about priorities. You can result in lower priority tasks can be starved of processor time.
Oh yeah.
Yeah.
And maybe one final mention about the UI thread is that the UI thread is very important in LabVIEW as a whole. Whenever a project is being loaded from file, so you double click the project, and if it's a large project, it can take minutes to load. That whole process, my understanding is that it happens strictly in the UI thread. And similarly, building an application as an executable, you go to your build spec, right click, build. And that can take minutes. And again, if the application is large, it can take 10 minutes, 15, half an hour. That happens strictly inside the UI thread. There's no multi-threading going on whatsoever. It's just in the UI thread. Just something to be aware of. And this is why, again, Darren Nattinger, in one of his presentations, he very rightly recommends, he says, if you want to reduce your project load times and your build times, you simply need to select a computer that has a very fast gigahertz processor speed, because again, building will happen in a single thread, loading from file is single thread. So the faster the gigahertz frequency, the quicker those actions will happen. So just something to be aware of.
Or keep the kettle handy.
Yeah.